today, what I'm gonna present to you is the federated learning. Many of you might be already familiar with the topic, but the three bullets and the three key message I would like to share with you today is what is federated learning and hopefully why we should care about it, and disclose how companies can adopt this new paradigm at the production level, and ultimately what can the developers or the people with the geek soul do today to take away something practical. All right, with that said, let's crack on. If we have to take a look at the overview of a AI pipeline, we should expect to have a model, some data, and a computing resources. And thanks to the three ingredients, we can basically train the model, right? At the end, we have a digital brain, if you will, that is able to take decision. Now, one of the concern that data scientists might have is that after a while, you just hit the limit of the informative juice contained in your data set. Let's say, what if you would like to build an COVID-19, let's say, detection algorithm based on AI, but you only have access to the data set containing the first version of the virus. You now heard that there are many variants of the virus circulating, unfortunately. But if we have a limited data set, there is only up to a certain level that we can use to instruct our AI model. So what happened when we hit the limit of the informative juice contained in our data? Well, we just plug in more data. And here's where the fun begins, because can we actually do that? So the challenge that federated learning is trying to address is exactly this one, the data access problem. So going back to the example of building the COVID-19 application, right, detection algorithm, imagine if all the clinical or all the medical institutions in the world, let's say all the hospitals in the world, plus all the private research centers and all the company related to the field would like to collaborate and share their own data to train a gigantic AI model to solve a specific task. So let's assume for a second that all the manager of these institutions are happy to agree to share their data for this purpose. Well, practically speaking, we wouldn't have a way to implement such a algorithm. We do have the model, let's say the AI topology. We do have compute resources. We do have data, but physically speaking, how would you practically move the data from all these institutions around the world in one place? You might bump into regulations. Think about GDPR that wouldn't allow, let's say, the same company, for example, Intel has offices in Spain and offices in Italy. And if each one of them is generating new data, we are not allowed to move that data outside the country where they reside because of GDPR. So how could you practically solve the data access problem at the scale level, especially when the data can actually make an impact in the algorithm that we were willing to train, like in healthcare? Second, even though there were no regulations, okay, let's assume for a second that GDPR didn't exist. So everyone would be free to move their data in and out as they prefer. How would you practically move thousands and thousands of terabytes and zettabytes of data, and where? Would you build a new gigantic location to host all the data and so that we can have a monolithic, let's say, presence? Who would be the owner of that infrastructure? It's just not doable. So the big question mark is, how can we leverage those data sets without compromising the sensitivity or the privacy of that data sets and being respectful at the same times of the regulations in place. The idea came from Google a few years back, is actually 2017, when they published this paper talking about this new approach that was originally thought for the IoT devices. In their case, it was a smartphone. Each one of us has probably a smartphone. It doesn't matter if it's not Android based, but the bottom line is that all our phones are basically data source, because we are generating data every day. I'm not thinking about whatever you might share with your closest friends or whomever you're in contact with, but think also about the log files, right? There is a mechanism in our phones that is keeping track of the functioning of the device, and that's getting updated regularly every second or something like that. So we are generating data as we go, and Google thought a way of leveraging that information without breaking the privacy of the user, but still taking advantage of the juice of the information contained in there. So they thought about a model where you would not share the data, you would just share the model. So we can think of the model as a digital brain kind of thing. We would clone the digital brain for each of these phone. Each digital brain would learn on the local phone using the local data sets. And then what we would take away would just be the learning of the model, not the data. If this was a little bit too technical, let me give you a step-by-step walkthrough on the process at big scale, because what Google did was in the first, let's say, attempt to federated learning. And but when we go to big scale, we need a little bit more robust infrastructure. So what you're seeing here is basically a pipeline with one institution, parameter server and aggregator is exactly the same entity. So it's just two different ways of calling it, but you think of it as the aggregator, which is easier. And then we have multiple institutions like the hospital we were mentioning before. Think about the yellow one to be the hospital in Milan, for example. The purple one is the hospital in London, and the blue one is the hospital in Hong Kong. Just making up cases here. So all the managers of the hospitals has agreed to build a COVID-19 detection algorithm using their own data sets containing all the variants and all the radiographies of capturing all the aspects of the disease. They already had an handshaking at the business level. Let's say they had a meeting. They decided to pull together the team of data scientists. So now we have at least one data scientist from each location, and they decide to implement federated learning. Well, in this scenario, how would it work? The three data scientists came up with a model, okay, which is this graph that you see here. Well, that stays exactly the same for all the institutions involved in the federation. So the aggregator or parameter server is just one machine, can be located in either one of these locations. It's thought to be a grid, but it's easily sorted. So the aggregator would kick off the process by cloning the model and sending a cloned version, so sending a copy onto each one of the institutions. So you see that the same model has been copied and sent over to Milan, London, and Hong Kong. Each one of these institutions would then start using their local infrastructure. So the hospital in Milan has their own machine, London the same, and Hong Kong the same. And they would train using the model as you would do normally, using their local data sets. At the end of the iteration, and this is a number that we can define, so n iteration, each single institution would send the updated model, which was trained with a local data set, back to the aggregator. As the name suggests, the aggregator is basically doing only one thing, is taking all these updated instructed version of the models and is merging them together, is joining them together. Since the model is the same, this basically reflects into a math average, as easy as it is. And the result of it is that we still have one unique model. To complete the training, we would just resend the model back again. Okay, so now here we have a model which is somehow containing the contribution coming from all the institutions, and that gets shipped over again. They would retrain again and again and again and again. At the end of the process, we have a joint model which has learned from 3 different institutions, and hopefully has converged to a good level of accuracy. Let me take another angle and give you an example which is outside the digital world. So hopefully it's going to be more comprehensible. Let's assume that myself, I'm seeing 3 names here. So let's assume that myself, Keisha, and Jackie are located in 3 different geographical area. So I'm in Italy, Keisha is in London, and Jackie will go to the Hawaii just for this experiment. We all have data. We all have one passion, which is AI, and we would like to attend a course which is delivered by the top professor in the region. And so I informed Keisha and Jackie that the Italian top professor will be delivering that course on that day at the given time. And we are all excited because we can attend that one. And then we would like to attend the one delivered by the professor, which is where Keisha is in UK. And then we would like to attend all of us, we would like to attend the course delivered by the professor where at the Hawaii. Unfortunately, all the 3 courses will be delivered at the same time. So there is a full 100% overlap. So we are not allowed to split ourselves because we cannot do that, right? So how do we solve it? And there is another major constraint that is actually concerning for us, because one of the rules of the course of each one of them is that we will not be allowed to share the content of the course outside that class. So what we end up doing is having a shared document like Google Drive or somewhere on Teams, and I will attend the course delivered by the Italian professor. Kasia will attend the course delivered by the professor in UK, and Jack, we will do the same with the professor at the Hawaii. And every 5 minutes, we just agreed that we are going to share our notes. So we're going to copy and paste our notes. At the end of the process, if the course is 2 hours long, and let's say each one of us is taking 2 pages of notes, at the end of the day, all of us will have access to a 6-page long notes containing all the contribution from the other courses. Now, what's interesting here, and that is the real parallelism with federated learning, is that the original content of the course was never shared. And so we were respectful of the constraint posed by the lecturer. What was shared was our own learning. So was our own takeaway of what was said during the lecture. And that is the important bit. In the federated learning model, what gets shared are not the data sets, are just what the model has learned from that data set, which is completely different, because what is learned is different from what is protected by privacy. One might argue that in the way I take notes is different from the way Jackie take notes, and is different from the way Kasia take notes. True, but that only applies to my example, because when it comes to federated learning in the AI domain space, the model is exactly the same. It has the same history for all the institutions, so the human bias is not there. All right, I hope this was clear enough. Now let's summarize what federated learning solves. It solves a lot of data access problems. So if you work for a company that has multiple offices around the world, and each one of those offices are generating data or just hosting a research environment, you likely bump into this data access problem, because you're not allowed to share data set among offices, although they belong to the same brand. But this is how you can leverage that information without breaking any privacy rule. At the same time, federated learning includes new threats, expose us to new challenges, right? Such as the federated learning doesn't protect the model, doesn't protect the training, and doesn't completely protect the data. So let me give you a quick hint on what could be the risk of adopting such a paradigm, because probably now you've realized how powerful this could be. Think about healthcare, but think about finance, right? Where banks have offices around the globe, they might want to take advantage of leveraging data sets from different locations to learn how the fraudulent behavior can be represented, right? Digitally. The risks are pretty much uncountable, because there are probably, while we are having this chat here, there is somebody working on the new kind of attack just to demonstrate that something can be broken. But and the job on the other side is to build defense wall that can handle those situations. But the two main immediate risk are the following one. One is the poisoning attack, and the other is the extraction attack. The poisoning attack is basically, it's about breaking into the federation and compromising the learning of the model, either by compromising the data sets or compromising actually what the model has learned. The other type of attack is the extraction. So because there is a lot of communication involved, since each institution will need to send the model updated to the aggregator, and then the aggregator will need to send that model back to each institution. I mean, we're talking about an aggregator that could be located in Italy and need to send stuff over to Hong Kong, right? It's a long trip on the network, right? But something is circulating on the net. So the extraction attack would see somebody intercepting the package at a given time and then waiting to see the same package at the next time step. By doing a difference between the two packages, they could infer something on the data set. With federated learning, these two attacks, which are pretty much common to any AI algorithm and environment, with federated learning, these two attacks will get amplified. Because if you think about breaking into a federation, one person with malicious intention might not need to break into all the institution of the federation. It might just need to break into the Milan hospital. Once it's in there, it would poison data set. Let's say if we're doing a COVID-19 detection algorithm, I would just add picture of trucks and cats, right? And call it COVID versus non-COVID. And that would affect completely the way that the network is learning. But look at this. Once I've affected the Milan hospital, because of the design, the aggregator would then merge this contribution together with the other one, and this would get reshipped over to all of them. And this is basically demonstrating that if you poison one location, you're basically propagating the poison over to the whole federation, which is not good. The other aspect of extracting data regards these three considerations to what does it take to secure a file. It takes confidentiality, so protecting the data and the model from the risk of exposure, execution integrity. So while we are computing something, I don't want anybody to interfere and extract information, and attestation. Somehow there needs to be a kind of a handshaking officialized at the beginning of the whole thing. At the digital level. To this extent, Intel has just introduced a super cool feature on board on the latest version of the server, which is actually rethinking the concept of a CPU. You're thinking of a CPU as your laptop or your server, but within that CPU now we have a solid ally, which is a kind of a protected environment where code can be executed in a secure way, in a completely encrypted way. We can use that protected environment to either extract our data or to train the model, securing the execution pretty much at all levels when it's local. On the network side, the literature is already fully populated with a lot of algorithms to encrypt and compress the information to send it over. So from that regards, there is already a wide literature that people can leverage to secure the execution. So Obviously, this approach can be implemented today on your own laptop and connecting your laptop with the other people's laptop. If you just want to run some, publicly available benchmark, that's totally fine. But for production level, if you want to do stuff in a secure way, probably SGX can be your best friend. All right, with that said, it's time to get real. I've introduced you the concept of federated learning and what problem it tackles. I've also shared with you some practical implementation for deployment level, such as the security aspect. Now, the question that some of the geek souls in this room that we might ask is, okay, how can I practically do this? Do I need to buy a box? Do I need to buy a software to do this stuff? No. There is an open source tool that we've released 3 months ago. It's called the OpenFL. As the name suggests, is open, and it allows you to build a federation like the one I explained to you. We're going to see a live demo in 1 minute, and I'm going to comment it through the execution just to show you all the components. But believe me, I'm also coming out in a few months with the video tutorials on how you can replicate the same demo, or how you can start your own federated learning network on your own machine, just to experiment for R&D or for actual production level. From the business perspective, there's some interesting bullets coming from Gartner, for example, that by 2025, half of the large organization will implement privacy enhancing computation. So that's extremely important. And then you see other 2 quotes talking specifically about the business growth that federated learning will bring to the table. Ultimately, before jumping onto the practical demo, I would like to tell you that we've already deployed such a paradigm at the big scale. Working with the University of Pennsylvania, we wrote down a paper, scientific paper, demonstrating the convergence of the model involving more institutions. We actually scale up to 7 times the size of ImageNet. So it's pretty cumbersome. And thanks to this collaboration, we now started a new collaboration involving 29 healthcare institutions around the world. So that's what we're working on. And it's all achieved through federated learning, the OpenFL. I will leave this animation while I'm pulling up the demo environment, but I will explain the animation in case somebody would like to know more. Let me open up a new session. I'll tell you what I'm doing. So what we're going to see now is an actual federation. So this is a live simulation. So apologize if something will break in the middle, but hopefully it will work smoothly. So what you see is the 3 black screens, right? While these 2 are still logging into the machine. Let me recover the connection. All right, here we are online. I'm logging in. This is a machine. Number 55 is the IP address. Okay, I'm now logged in. This is the machine number 50. Oops, number 50, nothing because there's no number there. Number 57, which is another machine. And this is the machine number 3, number 58. You can realize that these 3 are 3 different machines because this is AI demo 4, AI demo 3, and AI demo 1. Now, what I'm going to start, why did I pull up 3 different machines? Because I want to simulate an actual federation. So these 3 machines are simulating 3 different infrastructure located, for example, Milan and London and Hong Kong. So the first one will work as aggregator. So it's aggregator start. This one will work as a collaborator start. I've just called this collaborator 57, just to make it easy to remember. And this is collaborator 58. So let's start the aggregator. Let's start the collaborator. Let's start the collaborator 58. So this is sending task to collaborator 57 and collaborator 58 for round 0. These are receiving the task, meaning the model, and they are training on the local data set. You see how the local validation is being performed by saying the local accuracy is 0.0023, it ends by 3234, while on this side, it ends with other numbers. So the two institutions are actually training on local data sets, but using, and you can see how the model is actually evolving in a different way, because this is 074 ending by 207, this is 74 ending by 323. So they're actually independent. When they finish one round, they send back the metric to the aggregator, and the aggregator up here is basically computing its own accuracy level, because what we care about is the merged accuracy, not the local one. This is round number 4. As you can see, the information is going backward and forward. Now it's a little bit tricky for me to stay and block a specific line, but if you read from different rounds, you can probably spot all the details. So the merged accuracy is 0.8064. Here is 8059 and 8084. You see, when we merge them together, it's pretty much the average of those two accuracy. All right, while this is completing, it will finish up at round number 10. I think if you already have questions, we can already start answering those. And eventually, if somebody would like to have an additional point of view on how the process works, this is a very cool animation. So we have two institutions. On the right-hand side, the same infrastructure. Don't think of this as one single machine. Think of this as a big infrastructure, right? So here we have an infrastructure which is hosting the aggregator as well as a collaborator. And this is just an external institution, let's say it is. This is Milan, this is London, okay? So London is taking its own local data set and is using it to train the model. What model? The one that the aggregator has just cloned and shared over the two locations. So each one is taking its own local data, is training the model, is putting there, the aggregator is merging it together and is shipping it back. The result of this is this curve here up here, the accuracy is going to increase. And with that, I'm going to shut up and listen to what question you might have.